especially my friend Narayan for giving me this opportunity. So, first I start with uh, what is the essential, and you take a bounded linear operator T on it. It is essentially idempotent if T square minus T is compact, and operator minus identity should be compact. And third kind is operator minus an idempotent, where idempotent is such that its range and nullity of its subgroup should be infinite dimensional. Okay, so this is not recently published research, and so we aim to characterize essentially idempotent topics operators on using that research using theorem 1. We aim to characterize essentially idempotent topics operators on Hardy space and Bergman space. More specifically, we are trying to characterize the class of simple functions for which the topics operators are essentially idempotent. Okay, simple function, yes. So I'll briefly recall what is in the Hardy space. Hardy space is a collection of all analytic square integrable analytic functions on the unit circle. You take the arc length measure, normalized arc length measure, and Hardy space is it's a closed subspace of capital L2 for which the negative Fourier coefficients are 0. Okay, and you take this as the orthonormal basis. The monomial z power n, where n is a non-negative integer. You may take this as the standard orthonormal basis for the Hardy space. So if f is a square integrable function, P is the projection from L2 space to Hardy space. See, my domain is bounded analytic functions, essentially bounded analytic functions on the unit circle, and this is dense in Hardy space. It is not that the only bounded topics operator is associated with bounded symbols, and the only compact topics operators on Hardy space is the zero operator. Okay. So now we apply theorem 1, that is, we need to find those essentially idempotent topics operators on Hardy space. That means I am trying to characterize this function f for which the corresponding topics operator is essentially idempotent. So first kind means the operator should be itself compact. Second kind means I am just repeating the same result, and TF minus I, which operator minus identity should be compact, and third one is operator minus an idempotent should be compact. As I said, the only compact topics operator is zero operator, that is the only possible function f is constant function 0. So the essentially idempotent topics operator of first kind, the only possibility is constant function 0, and for the second, this difference is compact means the topics operator corresponding to the function f minus 1 has to be compact, but the only possibility is f minus 1 has to be identically equal to 0. That means f has to be the constant function 1. Now, so for first kind and second kind, we have only trivial functions, so we will essentially idempotent topics operators. So then we move on to the third kind. So if TF minus S is compact, if S is an idempotent with this property, then the essential spectrum of this topics operator should be the set 0, 1. So I mean, they obtain like this, any idempotent you can write it like this. Again, the same temperatures they obtain this. Any idempotent less, you can write it like this. V is a boundary invertible operator. This P of Rs is the projection onto R of S. Okay, I mean this projection essential spectrum is 0, 1. So this is a famous result by Ronald Douglas. Essential spectrum of a bounded topics operator on a Hardy space is connected. So before that, Harold Widom has proved that a spectrum of a topics operator, I mean bounded topics operator, is connected. So, I mean, Douglas proved that essential spectrum of a topics operator on Hardy space is connected. So hence there is no possibility for kind 3. That means if kind 3 topics operators existed, then the corresponding essential spectrum has to be set 0, 1, which is not a connected set. So the only essentially idempotent topics operator on Hardy space are 0 operator and identity operator. That means the simple functions corresponding to those topics operators for which the corresponding topics operators are essentially idempotent are only constant function 0 and constant function. For the case of Hardy space, it's like there is not much technical. It's very directly you can get. But when you move to Bergman space, the things change because there are topics operators with disconnected spectrum and disconnected essential spectrum. Also, there are non-trivial compact operators, and even it's a bit hard when we move from Hardy space to Bergman space. So, I will quickly recall what we mean by Bergman space. You take Dept into the unit disk and with probability area measure. And Bergman space is the closed subspace of square integrable functions on the unit disk with this probability area measure. And Bergman is the square integrable analytic functions on T. And let PA denoting orthogonal projection from L2 onto L2. And you take a simple square integrable function on unit disk. And you define topics operator like this, as in the case of Hardy space. Again, I take the domain as bounded analytic function on the unit disk. And this is dense in Bergman space. And bounded analytic functions form a dense subspace of the Bergman space. So, unlike in the case of Hardy space, there are unbounded functions for which, in Hardy space, only bounded functions give rise to bounded topics operators, but when we come to Bergman space, there are unbounded functions. Actually, it's a still open problem to characterize those functions for which the topics operators are bounded. I mean, there are class of functions, but to characterize such functions is still an open problem. And again, there are non-zero functions for which topics operators are bounded. Again, there are unbounded functions. Unbounded functions for which the topics operator will be compact. Again, that problem is also open. They haven't characterized. For bounded symbols, we have a characterization for compact topics operators, but for unbounded symbols, still it is open. So I'll come to that. It's connected to Gaussian transform. Right? So like last day, Shankar and Bohr mentioned about Gaussian transform. It's connected to that. So I'll quickly define Gaussian transform. Again, I forgot to mention both Hardy space and Bergman space are reproducive kernel. Examples of reproducive kernel Hilbert spaces. And that means the evaluation function is a bounded linear function. So that by application of race representation theorem, it quickly relates to Bergman kernel, and you take this normalized kernel. Let S be a bounded operator on Bergman space. So I define this B of S. Gaussian transform is a function defined like this. In the product x k is z, k is z. If S is a bounded operator, then Gaussian transform B of S is a bounded continuous function on unit disk D. Okay, so if S is a bounded operator, not that in the case of Bergman space, this reproduces normalized kernels converges to 0 weakly as mod z tends to 1. That means near the boundary, these normalized kernels tends to 0 weakly. So it's a necessary condition that if an operator T on a Bergman space is compact, its Gaussian transform should vanish near the boundary. It's not a sufficient condition in general. In fact, there are projections, infinite range projections, for which the Gaussian transform vanishes near the boundary, but the corresponding infinite range projections and which is called infinite range, so infinite dimensional. Then there are non-compact operators for which Gaussian transform vanishes near the boundary, but there are class of operators for which the converse is also true, that I will mention. Okay, so as we define for Gaussian transform for operators, we can define Bersin transform for integrable function. So it is like this: integral over mod k is under square, and it is meant by the definition way it is clear that Bersin transform of topics operator and the corresponding symbol are the same. By the definition itself it is clear. And few properties of Bersin transform. If E is good, then the Bersin transform is real value. If T is positive, then the Bersin transform is non-negative. Bersin transform of the adjoint is conjugate of the Bersin transform, and its mapping is a contract linear map from set-of bounded linear operators from Bergman space to eliminative functions. The last one is quite interesting. If you take a continuous function on the closed unit, the corresponding Bersin transform also belongs to closed unit. That means you can extend the Bersin transform of F to unities continuously, and on the boundary both of them are the same. No, we'll explain later. So then this is the converse what I was mentioning. So one more thing, as I mentioned, there are class functions if the Bersin transform of modulus f is bounded, even though the f is unbounded, the corresponding topics operators are bounded. Okay, so it's a case I think it was obtained by two mathematicians, Dept and G or something like that. Okay. So this is the converse. But if you consider the algebra generated by topics operator with bounded symbols, you take any operator of that algebra. For that case, compactness and the Bersin transform vanishing near the boundary. Both of them are equal. Okay. So in that case, S is compact and means the Bersin is equal to same that Bersin transform of S vanishes near the boundary. So now I mentioned that in the case of topics operators on Bergman space, there are topics operators with disconnected essential spectrum and disconnected spectrum. But he has obtained a class of functions for which, taking topics operator with symbol from that class, the essential spectrum is connected. So to define that class of functions, I define what you mean by Bergman metric. So you define like this, and you take the d of zr with output disk with respect to the Bergman metric, and you define the averaging function like this. A of dz1 is the area measure of the disk d of z comma 1, and if f is locally square integrable, then we get MO stands for mean oscillation. You define mean oscillation like this, this oscillation from its mean value, and BMO, actually BMO is the short form for bounded mean oscillation. We say a function is of bounded mean oscillation if this mean oscillation is bounded in the unit disk. And BMO consists of those functions for which this mean oscillation vanishes near the boundary. Actually, I have not written in the slide, this BMO and BMO definitely contains unbounded symbols, and these characterize those class of functions for which the angle operators are bounded as well as bound. BMO characterizes those functions for which angle operators are bounded, not only f, angle operator corresponding to f and f will be bounded, and BMO corresponds to those functions f for which angle operator corresponding to f and f conjugate. If both of them contain unbounded symbols. Okay. So using Bersin transform also we can define DMO and DMO. These coincide. This definition and this class of function will coincide. Using Bersin transform also, if this is bounded, then we say bounded mean oscillation. Again, if this quantity vanishes near the boundary, then we can say that function belongs to the DMO class. Again, some examples of declosure is properly contained in DMO. Not only also C of declosure is set of all continuous functions of closed unit disk is properly contained in this one also. And this one has a property that this is the maximal system subculture of L infinity such that this relation, this is known as semi-commutator of complex operators, TF minus TFT. So I mean, this is, I think this is work of KE, this is work of KE2, Professor KE2. Okay. So in this thesis, he has obtained that if F belongs to VMO intersection L infinity, the essential spectrum of corresponding topics operator is connected, and he has computed links. Gaussian essential spectrum is the range of Gaussian transform of this set, and beta is the strong check compactification of the unit disk T. And also there are topics operators of Boltzmann space with essential spectrum disconnected, as I mentioned earlier. So again, now we move on to characterizing the symbols for which essentially idempotent topics operators on Boltzmann space. Actually, so we have been, the problem is not settled. We have been work with Arun Kumar. So I thought of the problem, like, so whatever, we presenting whatever we obtained. And now we again come to the problem, and we have again, I'm repeating. First kind means the corresponding topics operator has to be from that topics operator corresponding to F minus 1 is from that. Again, the third one, topics operator, if the third kind is this operator minus an idempotent should be from that. So, moving, finding this class of functions, I define a set D. So as I said, we have a characterization for topics operators with compact, topics operators with bounded symbols. So D is a set of all bounded symbols for which the Gaussian transform vanishes near the boundary. And the corresponding, if the bounded symbol is topics corresponding to the bounded symbol is compact, if and only if this F is from this set D. And B contains all compactly supported bounded functions, and also it contains those continuous functions which vanishes near the boundary. So the first kind means if F has to be okay. One more thing, we are focusing only on topics operators with bounded symbols. Unbounded symbols we haven't done. And the topics operator is compact if and only F is from B. And the second kind means F minus 1 belongs to B. That means F has to be the set 1 plus B. The class of functions B and 1 plus B corresponds to essentially idempotent topics operators. And if you come to VMO intersection L infinity, the only essentially idempotent operators are those functions which belong to B and 1 plus B. Why? Because for third kind, as I said, as obtained in the case of the essential spectrum is F is in VMO intersection L infinity, essential spectrum of this topics operator is connected. In the case of if F this F is from this symbol, then you can't have the topic essentially idempotent topics operator of third kind. You are restricting the symbol to this class. The only essentially idempotent topics operator will be from the set D of 1 plus B. Okay. Now we move beyond this. We are looking for essentially idempotent topics operators of third kind for general bounded symbols. So what we did is we didn't know how to start and how to attack this problem. So what we did is like we took some idempotents with range infinite dimensional and multiplicity of adjunct being infinite dimensional. And we started to check whether we have some topics operator of third kind. So for example, we start with an example. I took a orthogonal projection with range and nullity being infinite dimensional. So for instance, you can take projection onto the En equal to, this is an orthogonal basis of A2 of the Boltzmann space. You take the projection onto the span of this. Varying number even integers, and one can directly compute and find that the Gaussian transform will tend to 1 by 2 whenever mode is at 10 to 1 by 2. Actually, this Bersin transform of this function, this Bersin transform is a radial function, and it tends to 1 by 2 as mod z tends to 1 by 2. So what we did is like, now we consider a function f such that its value is 1 by 2 on the boundary. Okay, and then there will be continuous functions for which the on the boundary its value is 1 by 2, and as I mentioned in the property, list of properties, the corresponding Bersin transform will be also has the value 1 by 2 on the boundary. So continuous functions on Bersin transform on the boundary, and the corresponding function will be the same on the boundary. So that means again Bersin transform is a function. So this difference Bersin, because this Bersin transform of T will also tend to 1 by 2. Transform of this difference should tend to 1 by 2 as. So now we claim that there is no bounded function G such that this difference, corresponding difference between this projection T and the corresponding complex operator is bounded. So for it, suppose that there exists such a G, then clearly as since Pg this difference is compact, then necessarily this Bersin transform should vanish near the boundary. Since Bersin transform of T tends to 1 by 2 near the boundary, Bersin transform of G should tend to 1 by 2 near the boundary. So what does it mean? Again, we have taken F to be like this, and Bersin transform of F and Bersin transform of G both tend to 1 by 2 near the boundary. Therefore, the Bersin transform of this difference tend to 0 near the boundary. So for complex operator, we have the converse plot like that. You can apply this result. Since the complex operator also belongs to this, we can apply this converse part. Converse part is true. Okay, so that means that this difference of complex operator is compact. So, but then what does it mean? Yes, this spectrum of these two complex operators are the same. But again, since this difference is compact, as a spectrum of complex operator with G, associated function G has to be 0, 1. That means SHS spectrum of this operator has to be set 0, 1. But again, this is not possible. Why? Because since S is a continuous symbol, only one knows this, each SHS spectrum has to be connected. Again, we can say that thus we obtain that there is no bounded function G such that the difference, this difference is constant. Actually, we are trying to find the class of functions for which corresponds to the essentially idempotent of complex operator of third kind. So actually, using the idea which I explained here, you can, if you are taking an idempotent with range of S and nullity of adjoint of S being infinite dimensional, such that its Bersin transform continuous extends continuously the boundary unit disk, then there is no bounded function of G such that this difference is compact. Okay, but there are idempotents S for which the Bersin transform do not extend continuously to the boundary of the unit disk. For instance, you take the singular inner function defined like this, and you take the invariant subspace generated by F, and if you are taking the orthogonal projection onto X, then the corresponding Bersin transform does not extend continuously to the point 1 on the boundary. And we don't know whether G such that this difference is compact. This difference is compact. We don't know whether if you're taking P to be projection onto X, still we don't know. We are trying to find whether such G exists. Yes, okay. Suppose such a G exists, G should have a property like this. On the boundary, Bersin transform of G should be 1. That we can easily obtain. and for z not equal to 1. And at z equal to 1, this limit, the limit at z equal to 1 of this function should not exist. These properties we have, and we need to check whether such g bounded functions g exist. I mean, that how much time do you have? 5 more minutes. No? 7 more. So this was stuck here. Actually, we don't know how to move further and try to find g satisfying this condition. And and we are also trying to find the properties of such g's. One thing is that b of this Gaussian transform of b of g is continuous inside the boundary, and except for z equal to 1, on the boundary its value should be 1. This much we know. No further. So far we haven't obtained any other information. So now I was trying to find the equivalence condition for essentially idempotent operators using the convergence of an increasing sequence of matrices. To consider a sequence of matrices A is of size n, square matrix of size n. As n increases, size n increases. We say sequence A converges to O n in type 2 if type 2 strong cluster sense if for epsilon greater than 0, there exists two positive integers. Constants, actually, there are constant positive integers depending only on epsilon. And after a state, like for n greater than n to epsilon, you can write an as Rn plus N. That means you can write an as a small norm perturbation of bounded rank matrix Rn. Norm of Nn is less than epsilon, and rank of Rn is bounded by n1 epsilon after a stage. Okay, after a stage, if you can split the matrix in this form, then you say An converges to N in type 2 strong cluster. Why the word cluster came is because if you have a sequence of matrices An converging to N in type 2 strong clusters, then it is possible if and only for each epsilon you need to find two positive integers, again constants depending on epsilon, n1 epsilon and n2 epsilon, such that except for after a stage, like for all n greater than n2 epsilon, except the maximum of n1 epsilon singular values, all other singular values lie inside the interval close 0, epsilon. Like as n increases, size of n increases, number of singular value increases, even then, except to very few, say at most a constant number, all other singular values should lie inside this interval close 0, epsilon. So this means so my result is that if T belongs to B of X, where X is a separable Hilbert space, is essentially idempotent, then it's a necessary condition that Tn square minus Tn converges to N in type 2 strong clusters. Tn is defined like this. You take the Tn to be the projection onto span of first n plus 1 base elements, orthonormal basis elements. If you can consider this like to be, if T is an infinite matrix, then Tn is first left, top left n plus 1 by n plus 1 border. Okay, so if Tn square minus Tn involving matrices, these preconditions are heavily involved. Okay, so if is convergence, and in the case of T self-adjoint, the converse is also true. So for this, we have to use a spectral theorem for normal matrices and the result by Argus, and I forgot to quote that. And so I'm using this. This is a bounded value function unit circle. Then if corresponding topics operator, this is a topics matrix. And by corner topics matrix, sequence of topics matrix converges to in type 2 if and only f is the constant function 0 and constant function 1. Because f is bounded real value means the topics operator is self-adjoint. And for self-adjoint, convergence and D essentially idempotent are equivalent. Right. In the case of RDS, we already know that only essentially idempotent topics operator are 0 operator and identity operator. That means corresponding symbols are constant function 0 and 1. The last So if this is a real-time function VM also, we have the same. Like this sequence of matrices converges to type 2 strong vertices if and only F belongs to B or F belongs to 1 plus B. So the problem is further problem. If S is an idempotent such that V of S does not extend continuously to the boundary of unit disk, then thus there exists boundary symbols F such that this difference is bounded. We can fully characterize the essentially idempotent topics operator on Boltzmann space. And again, check for essentially idempotent topics operators on Boltzmann space with unbounded symbols. As I said, there are unbounded symbols which give rise to bounded as well as compact topics operator, but there is no characterization for such symbols. And look for essentially idempotent topics operators. The same problem we can try it for other function spaces. And the last one is the converse part. If T is non-self-adjoint, whether this convergence implies that T is essentially idempotent. So these are the problems, and this is my joint with ongoing work with my colleague Arun Kumar. Thank you.
It's time for questions and comments. If there are no questions, let us thank you.
Thank you, sir. I invite the chair to present a token of appreciation to the speaker.
So good morning, all of you. We are working as an assistant professor at Calicut University. Experiences from and I have to learn and has published many research papers in this direction.
This slide is a map from unit to Felix. Okay, ICOST is not normal or analytic. And we can, it is possible to extend this idea in our setting that our research set psi plus some alpha square is sub to normal operator, and the psi is a mapping similar as in this to with vertices 1 minus beta square whole power minus 1, and it passing through plus or minus 1 minus beta square. And this model may help in the future to have produce lot and for this new process for cooperating. The static theorem of normal operator is the analogous way that is this. And another take many examples because we always usually equivalent to some other operator that is also subnormal. That is subnormal operator to search equivalence. Directly, if we are not able to check examples of subnormal force identify is it is equivalent to this application. And example for subnormal operator. The one there that is I hope this is a gateway of many research in this area of subnormal operator. Come at stop this lesson. Thank you very much.
Thank you for the talk of operators whose power the subnormal operators. Now, any questions from the speaker? No question. I have one question. You just said numeric normal extension is something unique.
Yeah. I guess it is the last case of answer.
I invite Professor V.D. Kiran Kumar, Assistant Professor, Department of Mathematics, Cochin University of Science and Technology, to introduce the speaker, Professor Dhruti Ranjan Dole.
Good afternoon. So our next speaker is Dr. Dhruti Ranjan Dole. So he is from IIT Dhaba. He will speak on CLT for fluctuations of space on the ideas of magnetic manipulation.
So, thanks to the organizer for inviting me to give this talk. So, I talk about St.Aloysius theorem for fluctuation of phase function for random Schrodinger operator which are magnetic field. So, we'll start with what is magnetic field, constant magnetic field. So, you take a skew symmetric matrix B. Other start with a skew symmetric matrix B and you define a function A from RD to RD. That A of x1, x2 dot xd is same as half this matrix into x1, x2, xd. So this component function AK is given by just the matrix multiplication of with this matrix Bj with that variable x1, x2 and x3. If you take the curl of this field, it will be constant. That's why it's called constant magnetic field. Now we will define what is magnetic Sobolev space. So it is collection of all function into L2. See, here lambda is open set inside RD. So you take all the L2 function such that it is the high nabla plus 8 called magnetic gradient. For those functions for which this magnetic gradient exists in the distributional sense. Magnetic gradient means same as Wood gradient, but so you take any function which is compactly supported, infinitely differentiable, compactly supported inside lambda. So we will say I nabla plus A of F is, let's each component at F1 tilde, F2 tilde dot dot F3 tilde. Then each Fk has to satisfy this integration by parts condition. Fk bar I delta k phi plus A k phi, and it will by similar relation like integration by y will be no, it will F same as F k phi dx. This is the distribution set. So you start with infinite differential function and do this integration by parts per line to satisfy by each component. This is the distributional set. Okay, therefore, of course, this if you take the L2 lambda d copies of this silver space, that is the standard inner product on that. So in this solar space, we can define a successful linear form with the core is given by this solar space. So what is Q of phi psi is inner product of magnetic gradient of phi and gradient of psi inner product. So this solar space will become Hilbert space with this enhanced norm. You have to subtract, you have to add the usual L2 norm with this evaluation, with the evaluation of quadratic form in this psi vector. Okay, with this enhanced norm, it will become Hilbert space. But there is a catch. If you take compactly supported function inside lambda and if you close it with respect to this norm, you will not get back this. Unless if it is a whole space or some. In general, if it is proper open set, this is closure of this CC infinity function just to this norm, we will call it WACL, and this will not be whole of WA lambda. Okay, this is the relation. So CC infinity function is sits inside WACL, it will be sit inside W of A and it is sit inside L2 of lambda. So on this W of A, we can restrict this quadratic form, and you can call this a Newman quadratic form. Similarly, on WACL, we can also restrict this quadratic form and call it Dirichlet quadratic form. This is same thing, inner product with gradient of phi and inner product with gradient of psi. So now, because of CC infinity function dense in del 2 RT, this Qn and Qd all are densely defined symmetric quadratic linear form. Therefore, and they are also closed, and these two are again complete Hilbert space with respect to this enhanced norm. So by standard theory in unbounded operator, these two will give two uniquely defined positive self-contained operator because these are positive. And we call it with respect to A, we will call it Newman Laplacian, and with respect to D, we will call it Dirichlet Laplacian restricted to a box. Okay, and the corresponding the Newman operator can be defined as standard Q of psi u should be psi into Hn acting on u, and this should be true for all psi inside this WA Hilbert solar space, and u should be inside the domain of this Newman norm. The domain can be defined. It is a set of all vector inside this WA such that Q psi u should be psi into some, there exists some vector u tilde, just that this equality hold, and this u tilde will be the image of u under this operator. Why it's called Newman and Dirichlet? Because if you don't want to go through this solar space, simply you can try it with core. So if you take suppose let's say Dn, if you take set of all function in L2RD such that is support sit inside, it is compactly supported inside this. With this core also you can define quadratic form, and you will get same HD. And if you take the set of all functions whose normal derivative is 0, and in this case normal derivative will be I delta plus A into u dot this normal. If you take all u such that satisfy this, and you take this core of this and define the same quadratic form, you will get same this Hn operator. Because of this normal derivative is 0 and CC infinity function, this is called Newman and Dirichlet. Okay. Similarly, with this Dirichlet Laplacian also we can define, but in this situation, this core will be WACL. The closure of CC function, CC infinity function is respect to that enhanced norm. Similar way, you can define the domain of this Dirichlet one will be there exists a u tilde such that Qd psi u should be psi u tilde for all psi inside this WACL. This u tilde is called the image of U under this digit operator. Okay, if you take the open set is whole or D, in that situation it will be equal. If the open set is full, in this situation, the closure of the CC infinity function will give the whole space WA RD. And in this situation, this Newman and Dirichlet will be the same operator, and it is denoted by I lambda plus A square. It is known as the free magnetic Laplacian. And the domain of this will be set of all U inside this WA polar space, such that there is a utilla Q of psi U should be psi utilla for all psi inside this polar space, and utilla will be image of U under that H of U. This is known as free magnetic Laplacian. Okay. Now we will define some random potential. So we'll start with IID random variable, where this collector is the index is over ZD. This for simplicity we will assume these are real value bounded distribution, and their common distribution is mu, and this U is a fixed function. So here we are taking U also bounded, of course measurable and compactly supported, so that I can make this V omega as a bounded operator. But all this theory goes if you allow with some rapid decay, then also it's good, but for the calculation simplicity we will assume this. So we have a measure mu on R, so you can take Z many copies of this measure space mu, and this by column graph we have this product measure space, forward space. So in this forward space, for each omega inside this big omega, we will define V omega is a multiplication operator by this function omega n and translation of U of x minus n, and this is a multiplication of by summation omega n U of x minus n, and phi is equal to, this is a simply multiplication operator, and since we take an omega n and U are bounded, V omega also will be bounded operator. Okay, now we can add this V omega with respect to this Hx A lambda. So when x is with respect to A, Dirichlet and Newman both, so just we add that with that Laplacian you add this V omega. Since V omega is bounded, so since this Newman and Dirichlet are self-adjoint operator, so since we are adding V omega is bounded operator, so it will be again a self-adjoint operator, and domain of this H omega will be domain of this Laplacian expression. But if he is not bounded, if you allow omega and have supporting whole arm, in this situation you have to work a little hard to show this is self-adjoint. This is not a trivial thing. Okay? Yeah, there is a standard if magnetic potential is 0. Professor one piece has a paper. There is a proof. What I am trying to say is V omega is unbounded, self-adjointness is not a trivial thing. This is also acceptable problem. So in our case, V omega is bounded, so we are in happy situation. Now, on this omega product space, we can just simply define Tn. What is Tn? Tn just is nothing but shift of the coordinate of omega. So if you take this Tn will be measure preserving transformation. Also, this is a good measure preserving transformation standard means polarity of T inverse of A same as polarity of A, and if A is invariant under Tn, then the polarity of A should be either 0 or 1. Okay. Also, we can define using that Q symmetric matrix B, we can define unitary operator. This is called phase transition, exponential of this function into translation of that function. So this will become unitary operator. Now, since we have Un and Tn, now we can see, we can actually see standard result that H of Tn omega and H of omega, they are unitarily equivalent with this relation. See, once we have this density of the operator, then we can define what is integrated density of state. So before that, because V omega are bounded operator and that Laplacians are positive operator, therefore this operator will be bounded below. So there exists M naught which will satisfy the standard bounded below condition. Also, these are known result for this this is this spectrum of this H omega lambda x, where lambda is bounded cell inside RD, so all the spectrum will be purely discrete spectrum. Since it is purely discrete and bounded below, if you put y is a finite real number, then if you take a spectral projection, this means and trace, this means if you count the number of eigenvalue of H omega lambda inside this minus integer, it will be finite, and it is called local integrated density, local finite volume integrated density of space. Now we will give the definition of integrated density of space. So if you consider this box minus L to L whole to the power d, means box cube around 0 with length L. Now we restrict that H omega to this box lambda L, count the number of eigenvalue, scale it by the volume of the box, you take the limit. So this side is a random measure, not probability measure, but this is random measure. It's saying if you take the limit, it will go to a non-random quantity, and it can be given by spectral projection of full operator, but you have to restrict to the box minus half to half to the power. Okay, and it should hold for almost every omega. So left hand side is a random quantity, but right hand side is a non-random quantity. So this distribution kind of function is known as integrated density of state. So this convergence we can write with just to take test function also, which is a weak convergence of measure. So if you integrate this to a both side, you will get, if you take trace of f of H omega lambda, f is compactly supported, so trace will be finite, then it will be trace class, and of course divided by the volume of the lambda L. Then if you take the limit, it will be expression of trace of f of H omega when it is restricted to the box lambda 1 means minus half to half whole to the power d. So this is also hold for almost every omega, and this we can treat as a analogous of law of large number. So we are taking some random quantity, this is random quantity, and it will be divided by this some scaling factor, and the limit is constant, so it's some kind of law of large number. So now we want to study what is their factorization. So simply we will subtract this from its expectation and try to find what is the distribution of their factor. So this kind of result in random matrix theory, this integrated density of state, this kind of limit is known as expected vector distribution, and there the study of the factorization is well studied and with very deep theory is going on there. So from there we take inspiration to study factorization of this. Also, let's define. So we will prove central limit theorem for this test. We will prove the test for when test function will be in this class. We need some decay of function, that function f at the infinity, so that this will become a test class. We need some decay of function for which it will become, if it is completely separated, of course it is test class. But if you allow f has support in the infinity, so we have to allow some decay in the f. So in our case, I will choose there is a decay for derivative as well. So now we will define the random variable y. What is that? That is trace of f of H omega lambda minus the expectation of the same random variable. So this is the center random variable. Now I have to study the factorization for this random variable. Of course, since these are bounded below operator, spectrum will be lies inside minus m naught to infinity for some finite m naught. Okay, so this is our result. So before that lemma in some first we have to we will prove if you take the variance of this random variable y and you scale it by lambda L, volume of the lambda L, if you take the limit, this limit will exist. This is a real number sequence. Limit will exist, and the limit will be independent of the boundary condition Newman and Dirichlet. Okay, and if we take, we are able to show this, that if f is monotonic function on this interval, then the sigma square f is strictly positive. So now we can define our result. So for any function with this in this class, means whose derivative and the function itself varies at infinity with some rate, if you consider this f of H omega L, by spectral theorem we can define f of H omega L minus its expectation, to scale it by square root, similar kind of thing in central limit theorem. If you take the limit, it will go to normal distribution 0 means variance sigma square n. So this is our result. Of course, if sigma square is 0 in some case, automatically it will go to some 0 random variable. So this is not interesting. So we will only consider where sigma square is. We will assume sigma square is greater than 0. So we will not prove directly for general function. So we will choose some class of function for which we have some tools to play around. So if you have unbounded operator, it is better to study with his resolver. That is bounded. In this case, because our spectrum lies from minus m naught to infinity, so we will take E is below this m naught. That is also invariable. So we will take this kind of Laurent polynomial with negative degree. But we need some that minimum of the power should be here because we need to have this should be trace class. So it has to be trace class, that the function should decay with some rate and infinity. If it is completely separated, it is fine. But if you allow, again you have to some decay, that decay should be here and it should be greater than d plus 1. Okay, so we will consider this. First we will prove the same theorem for this kind of polynomial, and if the exercise by St.Aloysius theorem, we can prove this is dense in the CC infinity function. Yes. Degree this m is not fixed. M is not fixed. If there is m, m should greater than this class. But E is fixed. This E is fixed. Okay. So by St.Aloysius theorem, we can easily show this is dense in CC infinity function. Okay. Completely separated continuous function. It will be dense. Okay, so now we consider the same random variable with this polynomial P. Where is P? P is inside this. So for each P inside this class, we consider the trace of P of H omega n. You subtract the expectation, you consider the random. So first we will prove the St.Aloysius theorem for this kind of function. Then there is a standard trick in probability you can extend. So same result. This is same result. So if you consider trace P of H omega L and subtract the expectation and divide by square root of lambda L, it will go to normal 0 and sigma square P. Okay. And again, this variance of this y random variable will exist as L goes to infinity. Okay. How will you prove this is? So how will you prove this theorem? So if you want to prove some central limit theorem, if you are able to write your random variable sum of some random variable, and then that sum if you have independence or at least asymptotic independence, there is lots of tools in basic probability theory itself. I learned from this book that I forget. There is a technique you can apply, you can directly apply. So you can object to write this random variable, or if you have sum of some equivalent sum of some other random variable which have independence. There we don't know, but we have to write this Billingsley. So how will you do that? So you consider this box. You divide that box into annular part. Okay, this kind of interval. If you write this, it will be in 2 dimensions. Easily you can see. This is in 2 dimensions. If this is your bigger box, just we are doing this kind of thing. Annular one. Okay? And we'll choose this. This collection will call some are denote B and some are small. In some sense, these are bigger box and these are smaller box in the sense that. So if you take all this box and take their union and to the closer, if you take the interior, you will get back this box itself. And why we are denoting some box are B and some box are S? Because you can see, if you consider the volume of the bigger box and sum it up, and if you divide the full box of volume, it will go to 1. And if you sum over all this, I call this smaller box, and if you divide it by the volume, it will go to 0. Later it will be useful. So only you have to deal with random variable associated with bigger box. Of course, these are simply one box, it will go to 0. This is the main idea. Okay, so given any box, what we divided, we will consider the same random variable associated with this box. Now we can check if B is fixed. Now we can check if as K varies, this collection is independent random variable. Because U is compactly supported, I noted one line. Here is this. Because U is compactly supported, if you restrict V omega in lambda 1 and V omega in another was lambda 2, if lambda 1 and lambda 2 at a distance, they will be independent. Because of this property, we choose this box such a way that at a distance, B is fixed, if K varies, these are independent collection of random variable again. If S is fixed, K is varies, these are independent collection of random variable. Then we will prove their moments, we can find their moments is bounded by the second moment of this random variable is bounded by the volume of the box. It will go volume as the volume order of the volume of the box, and the fourth moment will go to as the square of the volume of the box. This also we can do. It's standard martingale technique. We will apply, we will get this. And now if we have this, then we can able to show this random variable associated with the bigger box minus half of this random variable associated with the smaller box. In the second moment, it will go to 0. So I want to find the weak distribution for this random variable which associated with bigger box. But that is equivalent to find out the weak limit for this sum. Why I am doing this sum? Because in this sum we have independence. That is the main idea. Once we have independence, we can apply some standard trick to get CLT theorem. And there also, because of this convergence, the weak limit for this random variable associated with the bigger box will be same as weak limit of the random variable sum of this random variable. Again, because this volume divided by sum of the volume of the smaller box divided by the full box go to 0, because of this condition, these three random variables will go to 0 in the distribution. Therefore, we only have to find distribution for this random sum of this random variable associated with bigger box. So we have to determine what is the limit for this. That is the, and now here this collection are independent collection. Because as K vary, the lambda BLK1 and lambda BLK2 will be at a distance, and that distance is enough to claim they are independent. Because U is compactly supported. And for that, we will use this.
There's one question.
Yes, yes.
You've taken the function U, right?
Yes, U.
It's compactly supported.
Yes.
Is this distance bigger than the support of that?
Yes. Because this distance is order of N also, some fraction power of N. So they are enough distance to claim they are independent. Okay, so this is standard triangular array. You can find it in standard. If you have a triangular array ZLK for fixed L, these are independent random variable, and if it satisfies some Lindenberg condition, the sum of the random variable divided by the variance of this sum of this random variable will go to normal 0-1 distribution. Now exactly it will fit into our so we will define ZLK is YPD lambda B LK. See now if L is fixed, these are independent random variable, and because we prove the force moment is grow like square of the volume, that's why we can verify this Lindenberg condition. For delta equal to because of the volume estimate. So we can verify the Lindenberg condition when delta is 2. Therefore, we will have central limit theorem for this sum of this random variable. Okay, and because this variance of this sum, see here we didn't prove it, but if the variance of this sum is sigma square L, if you divide by the volume, it will go to some constant. We are calling this sigma square P. Now, because of this convergence of this random variable is equivalent to, if you scale it by what we call square root of lambda L to the power half, just rearranging, you can show this random variable will go to normal distribution is 0 mean variance sigma square of p. So we have central limit theorem for this Laurent kind of polynomial. Now we have to approximate for general function. That also we can do by this volume estimate, variance estimate. So if you take a differentiable function, the limiting variance of this random variable when function is not polynomial, any function which is decay little faster, the variance of yf can be given by upper bound, which can be bounded by the sup norm of f tilde. So f tilde is f dash x into x minus e to the power 1 plus d by 2. Okay. Now because of this collection of Laurent polynomial is dense in C, continuous function varies at infinity. So that's why we took f tilde as some decay, so that this f dash has some decay, so that f tilde is also decay at infinity. That's why decay needed for this derivative also. So we can find a sequence of polynomial from this space Laurent polynomial such that Pn will approximate this f tilde in sup norm. Once we have Pn, we can just integrate after multiplying this x minus e to the power this negative power with Pn. Just we can integrate this and we can get another sequence of function Qn whose derivative will be exactly this, and this Qn also will be in this class. Just we have to integrate power, the negative power will increase by 1. That's all. So we consider Qn, such that Qn derivative of Qn will be x minus e to the power 1 plus d by 2 into Pn of x. Once we have this and this result, we can apply this standard theorem in the probability theory. Suppose we have sequence of random variable xn and sequence of triangular random variable z and l, such that for if you fix l, as l goes to infinity, z and l will go to z and l. Okay, for fixed l, weak convergence happen for z and l. And again, now if we have l goes to infinity, so let's assume z and goes to z. Now if you verify this condition, this like convergence in probability between ZLL and XL, and we will be able to show that ZLL minus XL greater than delta after taking probability. If you show as L goes to infinity and L goes to infinity, if this becomes 0, then you can claim this XL will also go to Z. This is standard. Now we can just fit into this. So we will define ZLL is YQN D lambda L. So for each polynomial in this class, we know this ZLL goes to this ZL, because just now we proved that if you consider Laurent polynomial, this convergence happens. Now we'll denote Z is 0 sigma square m. Sigma square m is the limiting variance for this random variable x. Okay, so it is a real number sequence. If you take the limit for n goes to infinity sigma square n, it will exactly converge to sigma square n because of that variance estimation. Once we have that, you can easily verify. As Zn goes to infinity, Zn will converge to Z, where Z is normal distribution 0 means variance sigma square n. Also for each fixed n, as L goes to infinity, this is our result for when P is Laurent polynomial. So this also will again converge. Now we have to verify that probability estimate. So if you take YQN minus YFL and if you is greater than equal to delta, by Markov inequality you can write that expectation of this square divided by delta square, but this is same as Y just QL minus A D lambda L its square. Now again this variance estimate will give that bounding can be bounded by Qn dash minus F dash into this function, but this Qn dash is P and this F dash into this F tilde, but we choose Pn such way that Pn will go to F tilde in infinity norm. So as n goes to infinity, you can see this will go to 0. So we verify the three conditions of this theorem. So therefore, we can claim this random variable XL is YF D lambda L go to normal distribution with 0 means variance sigma square. So we prove the central limit theorem when condition is boundary condition is degenerate. But how will you prove for Newman and how will you show these are the same? So that also we can same kind of variant description will give. But if you take the Laurent polynomial, if you consider the random variable with degenerate and the random variable with Newman, their square they will converge to 0 in mean square. Therefore, they will converge to the same distribution also. And again, by approximation theorem, if this is true for P, we can show this is true for general function F also. Therefore, convergence of Newman and convergence of degenerate have the same limit. Okay. That's all I have to say. This is some related paper which have some theory for this magnetic field. These are some related paper, and this is Professor Warner piece is there. This is the standard paper when you want to show sum of two unbounded operators also self-adjoint. I will prove that. That is not a trivial thing. So these are the standard reference. And I want to say, apart from the random matrix theory, also for discrete Anderson model, this type of result also studied. So Pastur and Professor Warner piece studied in 2015. Then Pastur with her student, I think they studied, and Professor Nakano also studied this in this paper for some decaying randomness. Okay, then this paper are what I want to say, discrete model, this is enough progresses happen. Okay, so continuous case, there is one paper, yes, this one. This very long back, some Russian, I think, he proved this central limit theory for continuous model, but their random potential is given by Markov process, f of xt. And this is true for one dimension, but here our potential is defined. This is the only result for continuous case in dimension 1 with some specific kind of random potential. So that's why I want to do it for general D dimension with Anderson type of potential. That's all I have to do.
So in between you have this assumption that you has come then you relax
If possible, I think it's possible because I'm studying this paper by Simona Wargel. There they prove integrated density of state where U has support by some another approximation theory. I think if I able to understand how they prove that integrated density of state for where U have support, same kind of thing might do. But this is doable. One more approximation, you will prove C0 function, then from there they will approximate something. They did it, that's why I am studying this paper also.
Any other questions?
Yes. Yes, it's decaying. Settlement theorem, it is published. Oh, sorry, I didn't. So, Professor Nakano also studied with continuous model decaying randomness. Apology for that. Yes.
There are no more questions.
Thank you, sir. I invite the chair to present a token of appreciation to the speaker.
Thank you.
We will be having our lunch break now, and the next session will be starting by sharp 1:40.